So that makes sense. Not sure why the mass goes away, but the mass shows up as energy, so maybe that's all right. No charge at the beginning, no charge at the end. Seemed like everything works out okay. No baryons at the beginning, no baryons at the end. A plus one lepton and a minus one lepton. Everything kind of, especially if you make up that last one, everything kind of works out. And then you get the energy that's left over. There's a lot of energy missing, but we figured out those are neutrinos. And so you have the standard model of the sun. This is how the sun works. And so there ought to be this number of neutrinos. So you check, right? You have this standard model, you have this theoretical calculation that shows you what ought to be going on in there. And you measure, and you get half as many as you thought. So, what are the options?
First, you redo it, make sure you're not messing up the experiment.
Of course, the first thing the theorists say is the experimentalists screwed up the experiment. That's naturally their first move. So, off you go, right? And so they got to do it again. Somebody else has got to do it. They got to compare that. Yep. 20 years, sure. But yeah, 20 years later, nope. We did it right. Half as many neutrinos.
And you have to consider where they're going.
Before you get there, so one was you did the experiment wrong. Again, you work hard and you say, okay, nope. Two, sun went out. We don't really understand the inner workings of the sun as well as we think. It's not going on as it's going. We got to figure out the standard model, which involves why the sun is not producing as much energy as it used to, as we would expect from the outside. Why does that mean used to? Because it takes a long time for the energy from the center of the sun to get to the outside. And so it could be a long time before we realize, oh yeah, the sun went out and it's curtains. So that's a possibility, right? We don't understand the standard model well enough. Early on, it was proposed by somebody, they didn't actually know how to do the calculations, so I can relate. But we don't understand neutrinos as well as we thought. We create these neutrinos, but something's happening. And one of the ideas is that they can change from one to the other. It's called neutrino oscillations. This whole thing is called the solar neutrino problem, so you can Google that. You can Google neutrino oscillation, and that's sort of where they came down. They were able to look for the missing neutrinos, and I'll talk about this a little bit more later. The idea is it starts off when you have a proton that goes to a neutron plus a positron plus an electron neutrino, no bar on top. Comes out as an electron neutrino. It's an electron neutrino then, but then it changes. It changes to something else. So let's talk a little bit about how you would rationalize that and how you would measure that. But one thing you got to do is you got to figure out a way to measure other kinds of neutrinos. Because if it's changing from one to the other, we got to figure out what it's changing into and measure those. And we can put that to bed if we can measure those other neutrinos and say, oh yeah, all is well. The sun did not in fact go out, but these neutrinos are switching from one to the other. So I'll talk a little bit about the rationalization. I'll show you something that I tried to do to calculate this. We'll talk about why it didn't work and about why I'm bothering you with something that didn't work. Right? So. We talked, who remembers me talking about a particle in a box? More than once, okay, good. And we talked about how you can have this energy and this energy, but not in between, right? Is that what we said? That's what your chemistry teacher told you. That may even be what your physics teacher told you. They should know better. Why is it not true that you can't have an energy in between there? Why do chemists not want to talk about those? Why do physicists generally not want to talk about those energy states in between that particle can have just as well as the two that I wrote? What's special about the two that I wrote?
They're easy.
It turns out to be easier to analyze a complicated problem with those. Anybody?
Equilibrium.
Those are stationary states. They don't change with time. If I put it in E1, it stays there. If I put it in E2, it stays there. If I put it in halfway in between, it won't stay there. And in fact, if this is a charged particle somewhere between those states, it oscillates at a frequency dictated by that energy difference. And that's what I'm going to try to calculate here in a second, to try to understand neutrino oscillation. I've got those two energy states, and it's going to oscillate at a frequency given by those. And that's because of the way Schrödinger's equations work. I write down the wave functions, I add them, I square them, I find the probabilities. There's a cross term that goes like a cosine. So I can be in between, but if I start off there, if I put it in between, it starts oscillating from one to the other. Well, this neutrino state is like that one in the middle. When I create it, it is in fact an electron neutrino, but it is in a superposition of other neutrino states. And so it starts to oscillate between them. And at any given moment, if you try to measure what it is, it will be more or less likely to be any one of the three neutrinos. I'm only going to talk about two because it doesn't work anyway, so I have three. So that's where we're going to start. How do I talk about that change? How do I talk about the oscillation so that when it starts at the sun and goes at the speed of light to me, what is it so that I think I'm missing half my neutrinos? So it starts off here. We're going to have to do some relativistic physics here in a minute, but it starts off with the idea that the period of motion, the period of this oscillation between the different states when you're in a mixture of them, is h, Planck's constant, not h bar, but h, over the energy difference. So I've got to write down the energy difference of these two different neutrinos. Now, when the neutrino comes out, it has a certain amount of energy, and I'm assuming that it keeps that same energy all the way through. There's no mechanism for it to lose any energy. So it'll be in a given energy state. It just won't be in a stationary neutrino state. It will be in some mixture of neutrino states, and they will oscillate back and forth. Everybody get the idea? I got to find the energy difference between those two states, even though the same total energy, when I write it down, where is it? There'll be an energy difference between the different neutrino states. Total energy is the same, and I'm going to use that. Different masses mean the energy will be distributed in different ways. I don't want to talk about this. It's right here. These are not the two energy states. These are the energy differences between those, and there's going to be a total energy that's the same. Any differences you see are going to be a difference because of that. Essentially, it has to do with this statement. E squared is E naught squared plus PC. That's the equivalent of E equals 1/2 mv squared in relativity. If you're going really, really slow, this looks like E equals E naught squared plus 1/2 mv squared. The difference between them comes here, but the PC will also be different, so the total energy is the same. Did I do that? I don't have it. Probably did it on a different piece of paper. Let me start a different way. We're gonna get to the same place, but I don't have the notes and I don't wanna try to make that up in my head, because it's already bad enough. Another way that they rationalize this when they talk about it is that since they have different rest masses, they'll be going at slightly different speeds. And so the different parts of the wave function are moving at different speeds. That's actually not the right way to think about it. Another way to think about it is from here. Here, but I'm gonna do this. How many of you are freaked out by that function? Because we can start there. That's the wave function of a particle moving. You're freaked out by it?
Yeah.
Okay. Is it worth spending time on that? Yes, he says yes. All right, so then we're gonna do that. So I've written this in this room, have I not?
So it's just the plane wave, right?
Yeah, and that's absolutely true. But have I not? If I haven't, tell me I haven't.
I don't remember.
You have no memory of seeing that ever. All right, then, but you've seen this. No? I don't want this whole thing to stop just because I can't. If we can't start there, then we need to. I'm gonna do that. I'm gonna do they're moving at different speeds. What happens is, if they move at different speeds, this is for everybody who's not freaked out by this. If they move at different speeds, there's gonna be a phase difference in this function. And that phase difference is why you see why you have a different probability of detecting a certain neutrino and not another one. That speed, that's what's different. So we're gonna talk about how to find the speed of these different neutrinos. It's gonna be over there, but it's also gonna be from this. That's how fast I'm going. And if I have the same total energy and a slightly different rest mass, then I have a slightly different momentum. That means I have a slightly different speed.
Is gamma the same gamma?
Gamma, same old gamma. Gamma is 1 over square root of 1 minus beta squared. This is like a preview of 351. It's like extra knowledge for you. I can write this with this gamma as, let me tell you what beta is. P then looks like MC times beta over the square root of 1 minus beta squared. What is this? So beta is really the speed. It's just how fast you're going as a fraction of the speed of light. Just changes the units. If I take these two, I can get that beta squared is 1 minus E naught over E squared. And so that shows you right away that if you have the same energy and a different rest energy, you're traveling at a slightly different speed. And you can even calculate what that is, the difference in speeds of the two particles. The other thing is that you can see right away how fast are you going if you don't have a rest energy. What is your speed if your rest energy, the energy when you're sitting still, is 0?
Square root of 1.
Beta would be square root of 1, meaning you travel at the speed of light. If this is really, really tiny compared to your total energy, you're moving really, really close to the speed of light. So that's sort of what you already know, sort of conversationally. Beta then is approximately 1 minus a half E naught over E squared. Yes, it is. How did you know that? You just know that's where the smart money is. What have I got to do to get this? I got to take the square root of that whole thing and then recognize that E naught is tiny compared to E. Or claim that. Delta beta, which is the difference in speed between two particles, would be 1/2 E naught 1 squared minus E naught 2 squared, whatever they are. At E naught, rest energy, who remembers E equals MC squared? Yeah, it doesn't. E naught equals MC squared. E equals gamma MC squared. You can get that from here. This E
Does that say E naught 1 squared minus E naught 2 squared?
E naught 1 squared minus E naught 2 squared. Yeah, I've got two different particles differing only in their rest energy, i.e. their mass. So here we see that if these neutrinos are massless, if they have 0 mass, how fast do they go? These neutrinos have 0 mass, and that was the conventional wisdom. That's what both of those books say. Near as we can tell, there's 0 mass. Well, definitely the iceberg, I think. Dunlap says that they probably have a mass, but that's after all this. If they have no mass, if M is 0, E naught is 0, how fast are they going?
Speed of light.
At the speed of light. And they're all going at the speed of light. So we would never expect any oscillations. If the probability of detecting it as an electron neutrino here is 1, it'll be the same as the Earth. How do they change? Because this electron neutrino state is not stationary, it oscillates, and it oscillates according to this, and it depends on delta M squared. I was pretty happy about that when I saw that, because that is in fact what you read, is that the wave function oscillates at a frequency dictated by delta M squared. The change, the difference in the square of the mass, not the difference in the mass. And that's what they measure. By knowing how many electron neutrinos have turned to something else, they get this number. And that's how they put a bound on those neutrinos. They really only know the neutrino masses. They don't really know it's below some value. So, and if I multiply, if I find delta V over V, that's delta beta over beta. That's the fractional change in the speed. Okay, well, beta's almost formed, so it doesn't really matter. I haven't really done anything. Delta M squared, the difference in the square of the mass. Then, if they travel, what do I get? So neutrinos are formed here in the sun. They travel to the Earth. They travel 1.5 times 10 to the 11th meters. They traveling at a speed of about 3 times 10 to the 8th meters per second. So I know that that's going to be a time of 500 seconds. And we get to there. This is not actually exactly what I did in my notes, but if this difference in velocity over velocity is such that the 500 seconds it takes you to get here how do I get there? I need that phase difference. Yes. You can ask me too, or you can ask me and ask her if she understands it.
Ask her if she understands phase difference.
Yeah, it's okay. I'm trying to get around that.
Okay.
So let's see if I can do it without talking about phase difference. Because it's really in that way function, but I don't want to talk.
Okay.
If you want to do it, what's good. If we can have you talk in a normal tone of voice, I don't know what you want to do.
I don't know. I kind of want to save my energy right now.
You can always talk to me. We don't have to whisper. You can always talk to me and stop me and say, dude, nobody knows what you're talking about. It's not gonna hurt my feelings.
Thanks for clarifying.
So, if we could talk about that phase difference, then I would talk about a change inside here. But I'm trying to get around that. And I'm almost home, right? This is the difference in speed, that's the speed. Let's see if I wrote it, what if I wrote it this way? Delta V over, the speed is the distance it travels. Now see. Speed is C. And I essentially need this speed difference to be such that one of them arrives, if it's traveling with this slightly different speed, slightly different. It needs to oscillate in phase. No way around it. I'm gonna show you if I could figure this out, or if we do it with the phase difference. Here's where I wound up. Delta M squared, which is right there, is of the order of h times the energy of the neutrino over the distance it traveled times the cube of the speed of light. And if I can think of a way to get there without, or if I could do that, or if I can find a way to get there without it, or if I can find it written down here somewhere, it's here, I just don't want to waste forever. Again, what's nice is that I got the dependence I was counting on. I was happy about that. That the difference in speed of the different neutrinos goes like the difference in the square of their masses. And it happens because the square of their masses happens right here, and that's really the only difference. They're moving a little bit slower or faster. That's why they take longer to get here. They're going slower or faster because they have a different rest mass. It's incredibly tiny compared to this, but it's enough to slow one down relative to the other, so that when they go 150 billion meters from the sun, their wave function has changed just enough that now you don't measure that, the electron neutrino, you measure another kind of neutrino. If you calculate that, you get I dot 10 to the minus 83 kilograms squared. And again, that's just plugging and chugging. And the minimum, if you have two particles, if you know the delta M squared, then the minimum mass is one of them has at least that mass. I'll talk about that in a second. That I can actually do. So, if the difference in the squared mass is this, then one of them has at least that mass, if not more. So the minimum mass of one of them, the other one could be 0, but the minimum mass of the other one is the square of that. Or 3 times 10 to the minus 42 kilograms. Which is about 10 to the 12th times more massive than an electron. And about, no, sorry, yeah, 10 to the minus 12 times the mass of an electron. That's okay, they're pretty massless, right? So maybe that's all right. But everybody else says that that number should be more like 10 to the minus 35 kilograms. So 1/1,000,000th. Not 1/1,000,000th of 1/1,000,000th. Electron has a mass of half an MeV per c squared. Neutrinos supposedly have a mass of a few eV per c squared. So 1,000,000 times smaller, but this calculation gets 1/1,000,000th of 1,000,000th. So like I said, it doesn't work. But we can do the other one. I was working on this. This is something you read in the Wikipedia article. If delta M squared equals K, some constant, right? That's the number you measure experimentally and that I tried to match theoretically. I tried to calculate that on this bonehead calculation that I did. But if that's true, this is the difference of the two squares, so that's M2 minus M1 on the M2 plus M1, that's equal to K. If I assume that M2 equals M1 plus some difference delta, get that in this form. I can find out that delta equals minus M1 plus or minus M2 turn out to be plus or minus the square root of M1 squared plus K. And in fact, it has to be plus. You have to take the positive square root. So that says that if M1 equals 0, M2 would be square root of K. And they get that number, which is what they get from the experiment where they try to measure the phase delay in the neutrino wave function from the sun to here. We'll do that phase delay in 351. We got to do wave functions all the way through. And that's the basic wave function to get things from one place to another. That's how in quantum mechanics you go from place to place. But we should have done a better job of that. The one thing is to go from here to finish that out, to get here. I got this several different ways. So I think this is probably okay. Wrong, dead wrong. But I think that's a reasonable calculation of what I tried to calculate.
Where did the H come from in that delta M squared? You say in the bottom, it seems like you just pulled that from, I don't understand where that H
That comes from here. That's where the H came from. Or, when I do this is me and him having a moment, just so y'all know. If I write K, I can write E, V in terms of, distribute that K, I can write that in terms of omega, or I can omega as E over H, K as P over H, and it comes in there. That's really the same thing. That H happens when you try to connect an oscillating system to cause transitions in
So,
between
but,
two
but
energies.
that T right there,
Period.
that period, that's more like maybe some sort of coherence length or something. It's I don't, because I mean in the energy time uncertainty principle, that's where you're fundamentally saying.
Yeah, and
that
I fundamentally
is-
disagree with that, so
I'm sorry.
I'm really not saying, but I get your point, go ahead.
You're not saying that, but that T must be some sort of coherence time or something, or associated with some sort of coherence link.
Sure, but I mean, it's, you're making it sound fancier than it is.
Okay.
You add two wave functions, they each have, they have this term. And when I have two different energies and I add those terms, I get a cosine that oscillates at E over H. And so it's that kind of coherence term in that sense. But I mean, they're neutrinos, they're in a coherent wave function all the way, well, from the beginning to the, wherever they disappear, but. So yeah, I agree with it. I agree with that characterization, but it really is just the frequency of oscillation between two different states.
And so what you're saying is somehow where this derivation sort of went south is that we can't figure out how to get from that delta M squared is about equal to HE over DC's cubed, or?
No, I got that.
So you got
a couple
that,
of
so you
different
know how
ways.
this comes from.
I got this a couple of different ways.
Okay.
It's just you're off by like many orders of magnitude.
I see. Okay.
The problem is not that I did algebra badly, it's I did physics badly.
Okay.
I guess the take home is the sun didn't go out. I hope that came through. Okay. All right, so that's as much as I want to say about decay and reactions. So, next I want to get to ultimately elementary particles. Start just rehashing a couple of things that I think we did already talk about, which is comparing the different forces and how that can be a little ambiguous depending on what you choose to compare with what. So if I put two protons a distance d apart. And again, this is, you've seen this before, so you don't even have to write this down. But if I calculate the strength of the electric and gravitational forces, that turns out to depend on these two fundamental constants, the K that comes from Coulomb's law for electrostatic forces and the G that comes from the gravitational force. And it depends on the charge to mass ratio of those particles. And if I do that calculation, I get 1.2 times 10 to the 36. So electric force way, way stronger than the gravitational force. If that were all legible, it would be an F. As you go to table 17.2, he shows 10 to the plus 38 as that ratio. Do the same thing for 2 electrons. Why do you imagine you would get a different answer?
Different mass.
Different masses. Do it for a proton and an electron. Do it for a hydrogen atom. You get yet a third answer. They always come around that 10 to the plus 30 something. When I do the electrons, I got 10 to the 42. So the take home that the electric force is so much bigger than the gravitational force, which raises the question, why do we only notice gravity and not so much electrical forces? It's paradoxically because the electric force is so strong. This is strange, given what we just wrote. Why don't we see a diproton? What would the reason be for not having a diproton?
Electron absorption.
The only way to get them to stick is that they would do that. But a proton, okay, a proton when they jam together could possibly convert to a neutron. They can't separately. So it'll do that. The problem is, why don't we see a dineutron then? When you look at that, you might naively think, okay, well, clearly the nuclear force is weaker than the electric force. But that's not true. The reason that you don't get a diproton or a dineutron, we're going to find out, is that they can't get close enough to bond. And it's not an accident that it only happens when the two particles are identical. If the two particles are different, they can get close enough to bond. But if they're identical particles, they can't get close enough. One of the weirdnesses of quantum mechanics is what makes that happen, and that's one of the things we're going to talk about.
What do you mean by identical?
Identical, as 2 electrons are identical. They're absolute twins. You cannot tell one from the other unless one's over here, one's over there. Then you can tell. So 2 protons are identical. They're absolutely identical. They're distinguishable if one's over here and one's over there. Problem is when I bring them close together, I start losing my ability to distinguish them. And I guess I should have said indistinguishable particles. They become indistinguishable, and that's why they can't get close enough to bond. So identical means identical in every way. They have all the same properties, same spin, same charge, same mass, and so on. If you look at figure 17.5, the scattering cross section per unit solid angle, this goes way back to the beginning. That number is of the order of 10 to the minus 2 barns. Barn is 10 to the minus 24 square centimeters. It's big because most differential scattering cross sections are really small compared to a barn. So a barn would be really, really big, easy to hit. That's where that comes from. That's why they call those barns. True story. Something with a one barn scattering cross section would be gigantic. No internet. They had to amuse themselves. 10 to the minus 26. We have said very often that the cross section is just a ratio of two numbers. It has units of area but need not compare to the physical area. But if you do that anyway, then the size of the thing will be of the order of 10 to the minus 26 centimeters squared, which is 10 to the minus 13 centimeters, which is 10 to the minus 15 centimeters, which is about how big you think of a nucleon as being, 1 femtometer. Now, the question, what are we talking about there? What is that size? Are these little spheres? Well, what are they supposedly made out of? Nucleons. If you Google it, what do they tell you? Made out of 3 quarks, right? And what are those 3 quarks? How big are they? Or as we know, those are point particles. They do scattering measurements to see that. That's how that first clue started happening. They were bouncing stuff off of them. They said, oh no, it's not a sphere. It's 3 tinier little things. This is like roughly how far apart they are. There is no there, right? I mean, it's empty space. Everything's completely empty space. It's not even mostly empty space between the electrons and the nucleus. The nucleus is also empty space. So, this is some kind of a size that corresponds to some scattering cross-section. It's some sense of the size of the object, but it's not like there's a hard shell when you get there. That's the range of that's also the range of the force, and so this size that we get from scattering is also the range of the nuclear force, and so that's the sense in which things must touch before they interact. That's the phrase, I've been using that phrase, you know, like in the problem, right? One of the exam questions was, how do you get to the proton, how fast does the proton have to go to touch the nitrogen nucleus to start the reaction? That's what we mean by touching. So that the center to center distance is of the order of the interaction range, the range of the nuclear force. The nuclear force is attractive. You can think about that in the sense that it holds things together. Right? I mean, that seems reasonable. The other thing, the way to think about that though, is that the volume force reduces the energy. So we know F is minus delta U over delta X. That's how we define potential energy. So if we reduce the energy, if this delta U is negative, then the force holds them together. It's like the difference between being in a well and being in the top of a hill. Unstable, stable. Order of magnitude, MeVs per nucleon is the binding energy per nucleon, and that happens when you go over a distance of about 1 femtometer. The difference between no interaction and stuck is something on the order of 10 to the minus 15 meters. That's about 1,200 newtons. doesn't seem like much, but that's, for a proton, that's a pretty big binding force, 1200 Newton force to get loose. That's the force I gotta exert on a nucleus, on a neutron to pull it out of there, a proton to pull it out of there. If I'm just talking about the volume force. The nuclear force has a range of about 10 to the minus 15 meters. It's attractive. It has about that magnitude. How does it depend on the charge? Certainly not in any significant way, right? Neutrons and protons behave pretty much the same in that context. One definitely charged, the other one at least not with no net charge. So the nuclear force doesn't depend on charge. He talks about how it saturates. Tell me this. If the energy being this far apart is reduced, why wouldn't they get closer together? When I put in 2 neutrons or 3 neutrons or 2 protons and 2 neutrons, they hang around right there. What don't they do? And in fact, those are quarks. Those are quarks, so why can't they just do that? Why wouldn't they just do that? There's got to be some sort of short range repulsion. I put repulsion in quotes because it doesn't have to be an extra force. It could be simply a property of quantum mechanics that says 2 identical particles will either tend to clump together or try to repel one another. Based on no force, just based on the product, the idea that the wave functions have to behave in a certain way. It's a rule of quantum mechanics, if you want to think of it that way. It's not like one of the 4 forces that we could talk about that's making them do that. But it acts like a repulsion. I'm not sure I know how to get through the rest of this without talking about the spherical harmonics. So I'm going to try to moderate that. But we're going to wind up talking about those because the second simplest nuclear system. Anybody think what it is? The second simplest problem in nuclear physics. Simplest is a tie, proton and a neutron. But we've alluded to the fact that they're really the same thing. They're 2 states of a different wave function. One's the proton state, the other's the neutron state. So if we call that a tie for simplest, what would the next simplest be?
Those bonds.
2 of them together. And we know that we don't see a diproton and a dineutron. We waved our hands at that, but we haven't seen them yet. So that's your second one. Binding energy. 2.2 mega electron volts. What's the binding energy per nucleon? 1.1. How does that compare with the average?
Really low.
It's pretty low, right? Helium has like 8. It's around 2 per nucleon, right? It's twice the bonding energy. You plot that in your packing fraction curve, you are not hardly bound at all. That's very weakly bound as nuclear systems go. We're gonna do the wave function on that and sort of understand why that is. It's in the state, it's in the 1 plus. I have I here, I understand that. It should be J. Spin 1, 2 spin 1/2 particles in the spin 1 state rather than the spin 0 state. It's got a dipole moment. Of 0.86. Quadrupole moment. I always spell that one wrong too. 3 times 10 to the minus 31 meters squared, and that's normalized to the charge. The charge radius is 2.1 femtometers, and so the point of all that, as he's writing this, is any model we come up with has to, those are the kind of things you have to explain. You have to explain, why is it so weakly bound? Why is it spin 1 instead of spin 0? Why is it positive disparity? Why does it have these particular values? Why is the charge radius 2.1 femtometers? You've got to explain all of that. The wave function is not spherically symmetric. Tell me what you see up there that explains why it's not spherically symmetric. Here's your hint. Doesn't really answer it, but it's kind of a hint. Who remembers what those YLMs are? Some of you do, but in fairness, it's not because I tried to teach you. What are the YLMs? What do they depend on? Who remembers what L is? It's the orbital angular momentum. And in quantum mechanics, that tells you that your wave function has an angular dependence. It either depends on the angle down from the z-axis, that's the L, or the angle around the z-axis, that's the phi. And mathematically, it just happens when you solve that differential equation. Physically, it's our way of describing what the universe does. We don't really know how it does it. But if you have an angular dependence, you have an orbital angular momentum. If you have a phi dependence, so generally speaking, if you have an angular momentum of any type, you have an angular dependence. Whatever this force is that's holding them together, it's not spherically symmetric. The force that's holding them together is whatever it is, it's making these align their spins, which they would not prefer to do. They would rather cancel them and be spherically symmetric. That's what happens for the electrons up there. They want to have a spherically symmetric wave function. Who gets their way? Who always gets their way on that table? To have a spherically symmetric wave function. One's on the right.
So the noble gases.
Those are the noble gases, not Nobel, noble. Those are the noble gases. They have filled shells. They don't have an extra P hanging around that has a 3/2 L = 1. S shells, some of the ones over here, if you have a filled S and nothing else, that works, right? They have a spherically symmetric wave function. But some don't, and it kind of depends on how many electrons and whether they have an extra spot in the shell, just like in nuclear physics. So the nuclear force is not spherically symmetric. It has a preference for some states. We saw that also because the only way to fit data was to include that. Who remembers what S dot L was? S stands for spin. So that's the spin. Who remembers what L was? L stands for angular momentum. I don't know why it's L. I don't know why it's L. But that's orbital angular momentum. That's spin, which we think of as something spinning in place, but apparently that doesn't work. We saw that. There was a term, we had to include that. And it's actually even pretty strong. What's our evidence that that was really, really strong? Because neither S nor L by itself was conserved. I could swap spin for orbital angular momentum and back and forth. What was conserved? J, which was the total angular momentum. That was conserved. But that meant that I had to be able to change L to S and back. These are not conserved, but that one is. But the only way you can change L or S is to exert a torque. So this force has to exert a torque. It has to exert a force that causes rotation. So it can't be spherically symmetric. It's not like gravity, which is a central force, doesn't exert a torque. It's not like the electrostatic force. Okay, I'm trying to figure out how to wave my hands over all of this. Because it's just too much. So I'm going to look at in iceberg, sample 17.1. So for reasons that I'm going to belabor, L is something like the square root of 6 h bar. Now that came from L equals square root of L plus 1 h bar. L was 2, no 1, no 2. L equal 2, that's a It's a D state in that example. So if you have a particle that's going around in a circle of radius r with momentum p, it will have angular momentum p times r. So the idea here is I got a particle in a circular orbit, size r, momentum p, so I can look at this and say, well, I can figure out that p is of the order of square root of 6 h bar over r prime. You can also get something like that if you say p r prime is of order h bar. Anybody recognize where that comes from? That looks like the uncertainty principle, right? It's a very hand-wavy idea about the wave function of the uncertainty principle, but if I put it somewhere in this circle, then its momentum is limited by that. But that also tells me that r times p, which is L, will be of that same order.
Dr. Norwood, so is r prime just not equal to r? So it's like you place
Yes.
it somewhere in there?
It is. I mean, to within the hand-wavy level of what we're talking about here. R prime, you can think of r prime from this perspective, knowing the L, you can say, well, the angular momentum is p times r, it's the size of the orbit. So p has to satisfy that. Or you can use a hand-wavy uncertainty principle argument and say this product must be h bar. And so you get here. Kinetic energy is p squared over 2m. Which is 6 h bar squared over 2m r prime squared, which is 3 times his result. He has L equal 1. So the kinetic energy you would need to have that much angular momentum is 30. I calculate 30 megaelectron volts. For L equal 3, this is L equal 2. You would need 60 MeV proton to have that much angular momentum. So the point of that example and these calculations I did is that if you're limited by the energy, you're necessarily limited to the angular momentum you're allowed to have in that state. Even if you split it up, that's as much kinetic energy as you can have. That's as much L as you can have. When we, on page 630, by the time you get there, he starts using spectroscopic notation. So I made a few notes for myself, try to understand what he's talking about there. And it's L, J, 2S plus 1. So that's how you decode this. So when he refers to a 3D3 state, 2s plus 1 is 3. So 2s is 2. So s is 1. How do I get a 1 spin state out of fermions?
They have to be spinning in the same.
Yeah. 2 1/2s. And they have to, as you say, be spinning in the same sense. Right? They add rather than subtract. L S P D. L is 2. J is 3. It's the only one that's easy enough to see. So, if I could generate a 200 mega electron volt proton to bang into a nucleon to bang into another nucleon, see what's going on, I would then have 100 MeVs in the lab frame. And that means I would have enough for an L equals 2 interaction. $250 MeVs, that exceeds 30, which is the limit. So I can now look at L equal 2 states. I can see what L equal 2 states are available. He does not write a 3p3. Why not? The next step. Still on page 630, has a second note. So, why no 3D1 interaction? What is spin?
This would equal 1.
1. Triplet state, even under exchange. I'm gonna write that out in a second. I don't have good notes on it, but I'm gonna try to remember. What is L? Two. It's also even. What is J?
But as you
One.
draw there, it should be 1.
1, which is 2 minus 1. What does exchange mean? There's nothing for it except to start writing wave functions, but I'm going to try to write them in a way that's obscure but seemingly simple. So, how do you write a wave function? You start there. That's a wave function. That's called a graph. No, a ket. It's called a ket. And it's a wave function, right? It's just like when we were talking about particle in a box, and I said one of the wave functions does that, one of the wave function does that, same thing. That wave function is that. write it in that way. I then put something in there to indicate what I'm talking about. So if I'm talking about spin, a particle can be spin up or spin down. And so if this is particle number 1 and this is particle number 2, one of the possible states would be this, right? Nobody wants to say no because they know if they say no, I'll ask them why. Why can I not write the wave function of two particles as particle number 1 being up and particle number 2 being down? There's two of them. They're identical.
Can't distinguish.
You don't know which one is which. And I just said I can tell which is which. So I can do that. That's a possible result. That's also a possible result. So how do I figure out which one? I can't. So what do? I simply decide all I can ever do is write a sum of those, right? I can write it as this plus that, or I can write it as this minus that. So what would that difference be? Well, we got to go back and talk about those cuts and what they mean. So if I were to write, what this means is that when I take my spin operator and I operate on this spin up state, I get plus that number with my same state. I get that state back. What do you bet happens if I do that same operation but on this state?
Minus h bar over 2.
I get the same number but with a minus sign in front of it. Last step, and we're going to understand what the word even means. And that's where we're headed. We want to know what does that underlined even mean. And we're going to do it some other time. Come over. We need to know what it means to be even under a state. We need to find out that no fermion can have that state. Once we understand that what even means, we're going to understand why no fermion can have that state. That's what he says, and that's what I'm heading for right here.